Okay, so as in the last video we have discussed about the characteristics of the simple harmonic motion in very detail, right? Um, we discussed that if we have to check that the given motion is simple harmonic motion or not, we must apply these four conditions in order to check whether that given motion is simple harmonic motion or not. So the first one was always motion should be oscillatory, which means it must be periodic, it must be to fro, and the main condition of simple harmonic motion is it must be in straight line, right? So every points are included in this. The second point, some restoring force must act on the vibrating body. We talked about mass spring system, so there would be restoring force which will gonna take that body from its extreme point to the mean position, right? That is restoring force. Third, acceleration of the body is directly proportional to the negative displacement. Since acceleration is towards mean position and displacement is away from the mean position, that's why we have got negative displacement. So this is the main condition in order to check the given condition, the given motion is simple harmonic motion or not. The fourth, last but not the least, total energy of the system must remain conserved. In today's video, we will be discussing about the examples. In our course, there are three main examples of simple harmonic motion is given. Examples of SHM means simple harmonic motion, right? I must not write everywhere now simple harmonic motion. I must write SHM. So we have in our course three main examples. The first example is the connection between uniform circular motion and simple harmonic motion, or you can say this is motion of projection. We're going to discuss each and every example in very detail of particle along a circular path. See, motion of projection of particle along a circular path, or you can name this example as the connection between uniform circular motion and simple harmonic motion. The second example we'll discuss motion under elastic restoring force. Motion under elastic restoring force, or you can say Hooke's law. Here we're gonna discuss mass spring system. The third, the last but not the least, is simple pendulum. You all have heard about simple pendulum very much. Simple pendulum, right? So we're gonna discuss these three examples in very detail. We're gonna drive displacement formula, acceleration formula, velocity formula, time period, frequency formula for each one of them, right? In today's video, we are gonna discuss motion of projection of particle along a circular path, right? So our main topic is this today. So now see, I'm making a circle here so that I can explain you this. See how we have a connection between uniform circular motion and simple harmonic motion. I'll try to explain you this in a very simple way so that it must be clear to you, right? The concept must be clear to you. Now see, if I'm making a circle here, this is a circle, and here I am making a surface, right? So this is a surface, and here I have made a circle. Now I have made one particle. Travel on this, right? and now I am making light here. I have switched on the flashlight to see the shadow, of the particle. To see what? To see the shadow of the particle. Now see this point or particle, right, will move here. Its projection, for example, is here right now. Its projection is here for now. This q is its projection, right? So when it is moving here, now it has reached here, right? Its projection is here now. Now this point is here, and its projection would be here now, right? Now its particle is here and its projection would be here now. Again, now it will repeat its the motion. It will gonna go here, it will gonna go here, it will gonna go here, which means its projection would be here. It will gonna go here, its projection would be here. It will gonna go here, and again it will come here, its projection would be here, right? So this motion would be continued. Now if you see the shadow's motion, see this q1 is shadow, this one is particle. Leave the particle for now. See the shadow, right? This shadow will be moving like this. Initially this will go like this. If the particle will go from here to here, right, then this particle will go from here to here again, right? So this shadow's motion will again go from here to here, right? Now see what this motion is. Now this motion would be continued, back forth, back forth. Now you can see this motion repeats itself in equal interval of time, which means this is periodic motion, right? Which means this is periodic motion. Secondly, this motion is to and fro, back and forth, which means this is oscillatory motion too. Now see, this motion is in a straight line. It is in a straight line, right? So now our three conditions are applied. This is periodic motion since it is repeating itself in equal interval of time. It is oscillatory motion since it is periodic. In addition to the periodic, it is to and fro and back and forth. In addition to and fro, back and forth and periodic, it is in straight line, which means it is simple harmonic motion. The motion of the shadow of the particle is simple harmonic motion, follows simple harmonic motion. So what's the definition of it? Let's write definition of it. Now I hope how the projection or the motion of the projection of the particle along a circular path follows simple harmonic motion is clear to you. Now what's the definition of it? Okay, let's write with white, then we're gonna highlight it. Now see, the particle P is moving along a circular path.